Hello viewers, welcome to CEC lectures. Myself Dr. Preeti Chadbani. I am from Department of Computer Science, Arabic College, University of Delhi. So in our previous lectures we were going through the topic of concurrency, and we have also seen the meaning of serial schedules, and I have left with you a problem actually, which was who is going to maintain this concurrency if it is going to be left to the operating system. This is going to give us some more problems. So from there, we are going to take this up. So for a quick recap, just have a look at the screen, which is going to show you the two transactions T1 followed by T2, and this is one schedule. Another schedule which we have seen is this one, which is about T2 followed by T1, and in T1 we are transferring $50 from account A to account B, and T2 is about transferring 10% of amount from A to B. And these two schedules, which we have also seen in our earlier lecture, are basically known as serial schedules, because one particular instructions in one particular transactions are appearing together. There is no interleaving. Now, when we talk about concurrency, and we say that these two transactions are going to run concurrently, the question comes up, who is going to maintain, who is going to execute, or who is going to control this concurrency. What is happening here, if left to the operating system, then there will be a problem which says that your operating system may execute one transaction for a little while, then perform a context switch, execute the second transaction for some time, and it keeps on jumping between the two transactions, because the CPU time is shared among these two transactions. So if control of this concurrent execution is left entirely to the operating system, this is going to give us a problem, and this is going to, we can say, leave the database in an inconsistent state. So this was the problem actually. Now, what kind of inconsistent state I am talking about? In order to understand that, let us look at the screen, in which a kind of interleaving of the schedules, interleaving of the transaction is being shown in a schedule. So what is happening here? Three statements of T1 are being executed, then four statements of T2 are being executed, and this vertical alignment you can consider as a time, kind of timeline, I can say. Then some four statements of T1, and then whatever is left of T2 is being executed. So what actually happening here is, what actually is happening here is, this schedule is not a serial schedule. Why this is not a serial schedule? Because the instructions which are of one particular transaction are not appearing together. So here you can see 3 of T1, 4 of T2 are different. Similarly, 3 of T1 and 4 of T1 are different. In between, 4 instructions from T2 are being executed, and the leftover 4 instructions of T2 are being executed after the T1 is finishing. So this schedule is definitely not the serial schedule. Or we can have one more example of this non-serial schedule, which is shown on the screen, is two kind of two instructions. I am taking it in numbers just for the sake of simplicity. So two instructions of T1 in one go, then 4-5 instructions of T2 in another go, then a context switch is happening, and it is again coming to T1 executes whatever is left of this T1, and then again after context switching or through context switching is going to T2, and then whatever is left of T2 is being executed. So both of these schedules are definitely not serial schedules. Now, if this kind of situation we are going to leave to the operating system, this is going to give us, or this is going to result in an inconsistent state. So now the question was the whose job it is. So it is the job of the database system to ensure that any schedule that is executed will leave the database in an inconsistent in a consistent state, not the inconsistent one. So, database system is going to keep a check on that, that the schedule which is going to be executed should not play or should not compromise with the consistency of the database, and the concurrency control component of the database system carries out this task. So, the name of the component here is the concurrency control component, because we cannot leave this to operating system entirely. Now, this consistency of the database can be ensured. I am talking about concurrent executions, by making sure that any schedule that is executed has the same effect as the schedules that could have occurred without any concurrent execution. So, what I am trying to say here is, let us say we have a schedule which is concurrent and we have a schedule which is serial non-concurrent. Then in that situation, effect of both the schedules which and these schedules are for the same activity. So, one side we have concurrent schedule and another side, let us say we have corresponding non-concurrent serial schedule. These two schedules must have the same effect on the database, that is, the schedule should in some sense be equivalent to a serial schedule, and such schedules which are equal or equivalent to serial schedules, but actually they are concurrent, such schedules are serializable schedules. And yes, we can say that serializability is something which is important, which is desirable and which is inevitable for maintaining the consistency of the database. So, when we talk about the concurrency control, if you can recall the previous lecture, we started with the isolation is going to be disturbed because concurrent execution of the transaction is happening, and when the several transactions executed concurrently in the database are happening, then the isolation property is no longer, isolation property may no longer be preserved, and there are high chances of this particular scenario, and insurance of this disturbance of isolation property is going to create inconsistency. Now, to ensure that it is the system that must control the interaction among the concurrent transactions. This control is achieved through a variety of mechanism called concurrency controls scheme. And I have just told you that who is responsible for maintaining this concurrency, or who is responsible for this concurrency controls. It is the database itself, and the one part of the database system which is related to this concurrency control is responsible. Now, that part how is going to maintain the concurrency, or how it is going to manage the concurrency through variety of concurrency control schemes. So, we have concurrency controls scheme, and as with a general principle I can say, no one scheme is clearly the best. Each one is having its own advantages and disadvantages. In fact, we can have various schemes for this concurrency control thing, but the most frequently used schemes are two-phase locking and the snapshot isolation. The two mechanism which we are going to cover very briefly as per the scope of our course are two-phase locking and snapshot isolation. So, first of all, let us try to understand what is this locking and how this lock based mechanism is going to work. So, when we talk about lock based protocols, so lock actually is a we can say is a technique or is a mechanism to control the concurrent access to a database, to a data item or to object of a database. So, basically any data item can be locked, and this can be locked in two modes. One is the shared mode, which is denoted by the letter S, and another one is the exclusive mode, which is denoted by the letter X. in exclusive mode, that particular data item can be both read as well as written. This X lock is requested by using lock X instructions. So, the instruction for getting or instruction for requesting, I can say, this X lock on a particular data item is nothing but lock X, and mostly as the name indicates, it's an exclusive lock. So, when a data item is having an exclusive lock by a particular, we can say, transaction, no other transaction which is going on concurrently can access that data item for which the X lock has been opted by another transaction. So, for example, let us say I am talking about for uh, we can say for account A, the X lock is being obtained by T1. Then in this situation, T2 will not be allowed to access the access the account A, because that account is that account A is with transaction T1, and that too in the exclusive mode. Now, if we talk about shared mode, in shared mode we can say data item can only be read. So, if some data item has to be updated or we need to write something on that data item, exclusive mode or X mode lock has to be opted. And this S lock similarly, as we have seen that X lock is requested by using lock X instructions. Similarly, S lock is also requested using lock S instructions. Now, these lock requests, who is going to who is going to accept these lock requests? So, concurrency control manager, who is the database component responsible for management of this whole concurrency thing, is going to take this concurrency, take these lock requests, and the transactions can proceed only after the request is granted. If the transaction has made a request, the and we can say they have not been granted the request, then transaction cannot proceed, because proceeding of transactions is only allowed in case of the request is granted. Now, if we want to see the compatibility of the both locks, we need to understand this table which is on the screen. So, here we have in the first row, we have two kind of modes of the lock, S and X, and similarly on the we can say first column we have S and X. So, here this lock compatibility matrix says if if one particular data item is accessed by one transaction in S mode, another transaction can also take that data item in the S mode. So, S in the column and S in the we can say row are giving you a combination of true. So, one particular side, that is the column side, you can say for the sake of simplicity, one particular transaction side, one particular side of SX, let us say column side, is for one particular transaction, and another particular transaction is being, or the lock request of another transaction is being represented on the row side. So, let us say T1 is on the row side and T2 is on the column side. So, if one particular transaction T1 has obtained S lock, let us say for account A, the T2 can also obtain S lock, because please remember that in S lock the data items are being read only. While we jump to the next cell where T1 is asking for the data item account A in an exclusive mode through an X lock, then in that situation another transaction T2 will not be even allowed to have that data item in the S mode. So, the bottom line here is, if an exclusive mode lock is being given for one particular data item to a specific transaction, no other no other transaction will be going to have that data item, not even in S mode. Let this X mode is a different thing, not even in an S mode it is allowed. So X mode is not actually compatible with any of the modes, not with the X, neither with the X nor with the S, while here S is compatible only with the S. So one data item can be taken in the S mode by two different transactions, while if one particular transaction is taking a data item in the X mode, no other transaction will be allowed to, we can say, access that. And this type of thing is what we can say is a lock compatibility matrix, which is very important when we talk about these lock based protocols. So till this point we have understood what actually your uh, locking mechanism, how this locking mechanism is working, and so on and so forth. So a transaction may be granted a lock on an item if the requested lock is compatible with the locks already held on the item by other transactions. If the compatibility matrix is going to give false, then that lock cannot be granted. And not only the two transactions, but I can say any number of transactions can hold the shared lock on an item, but if the transaction holds an exclusive lock on the item, no other transaction will hold any type of lock on the item. Now, considering this situation, one concept which immediately pops up is about the deadlocks. So deadlocks we have also seen in our previous series of operating system, and you must be aware with the term deadlock. That means for example, transaction A is requesting some resources from transaction B. Transaction B cannot move because it is requesting some resources from transaction A. So now in this situation, what is the significance of deadlock here, and what kind of deadlock we are talking about here, how is it going to be implemented? For this, let us consider a partial schedule which is given on the screen. Now why I am saying that this is a partial schedule, because all the statements of a schedule are actually not shown in here. So we have taken two more transactions, we can say. One is T3 and another one is T4, and please see that these are going on concurrently. These are this is actually not a serial schedule, not a serial schedule at all. So if you can see, T3 has obtained one exclusive lock on the account B, which is given in the first statement, and after taking a exclusive access to B, it is reading B, it is doing some updation, and it is in the writing B. Now for example, the statement which is next, which is at the written at the end of T3 is lock X, lock XA. That means the requirement is of obtaining the exclusive lock on the account A also, but before that there is a shared lock on A which is obtained by T4, and with this shared lock, as the lock is shared, it is going to read the A thing, and now what it is looking for is lock S, which is the shared lock on the B item. So T4 is asking for the shared lock on A as well as on the shared lock on the B, while your T3 is asking for the exclusive lock on the B as well as the exclusive lock on the A. Now what is happening here? Please consider that is it actually possible? Is it actually a possible scenario with when we consider the compatibility matrix? Your T3 is already having X lock on B. So with this situation, when it has not been released, can we can we grant this S lock on B, which is given in the second last statement of this schedule, or we can say which is the last statement of T4 of this partial schedule. So, what is happening here, if we can see, neither T3 nor T4 can make progress because execution of lock S on B causes T4 to wait for T3, because T3 is in the is having the charge of item B in an exclusive mode, and while executing lock X on A is going to cause T3 to wait for T4 to release its lock. So, basically in this schedule what is happening, T3 is waiting for T4 to release the locks. T4 is also not able to move because it is waiting for T3 to release its lock. So, basically what is happening, both are in a kind of a deadlock situation, and neither T3 nor T4 can make the progress because execution of shared lock on B causes T4 to wait for T3, while execution of exclusive lock on A causes T3 to wait for T4. So, T3 is waiting for T4 and other way around also, T4 is also waiting for T3. So, such a situation is called deadlock. Now, both of the transactions are not able to, we can say, proceed, and in order to handle such a deadlock situation, which is given on the screen, if you can see and introspect it once again. So, with this kind of a situation, which is a situation of deadlock, in order to handle this situation, one of the transactions, either T3 or T4, must be rolled back and its locks should be released so that other one can proceed. Now, which one is going to release the locks and which one is going to proceed, that is another, we can say, kind of a policy decision which will be taken by the system itself. Now, this kind of deadlock situation is going to happen, which we can say the potential for deadlock exists in the most locking protocols, whatever locking protocol that's presently we are going through the protocol of two-phase locking. So, this kind of potential is also there is in two-phase locking, and in any of the locking schemes or locking protocols, deadlocks are are a high possibility, we can say. So, one thing here is who is going to be the victim, that which transaction is going to release its lock and got to go to the situation of rollback, which one is going to proceed from here onwards. And if another situation which is a kind of an evil situation is the starvation is also possible if concurrency control manager is badly designed. So, for example, a transaction may be waiting for an X lock on an item, while a sequence of other transactions are requesting and also being granted the S lock on the same item. So, for a particular item, one transaction is waiting because X lock is required by from it, and another transactions are continuously being granted and requesting, and there is a long queue for that particular item to have in the S lock mode. So, the same transaction is repeatedly rolled back because because it is we can say stucking in the deadlock. So, that particular transaction which is looking for an X lock is kind of in the starvation situation. So, what is important here is the concurrency control manager should be designed in such a way that these deadlock situations can be handled properly in order to prevent the starvation. Now, when we talk about these locking protocols or these locking situations, how these are to be implemented. For implementation of locking, there is a lock manager, and that lock manager is actually kind of we can say it's separate component or a separate practice or process. So, transactions can send lock and unlock request as messages to this lock manager only. and the lock manager replies to a lock request by either sending a lock grant message or a message asking the transaction to roll back in case of a deadlock. So, it is, it depends on the situation. So, it is the lock manager who is going to reply to the request. That reply could be sending or granting a lock request, or it could be other way round, in which your lock manager is asking for the transaction to roll back if there is a deadlock. And how this lock manager is going to kind of maintain this whole scenario by a memory data structure, by a in memory data structure which is maintained by the lock manager, and that is known as lock table. So, the requesting transactions will need to wait until the request is answered. So, either the requesting transaction is going to have that lock, or it will be kind of rollback because of the deadlock situation. And this, in order to maintain this whole thing, your lock manager is going to maintain a data structure which is available in the memory, and that data structure is known as lock table, and lock table is used to record the granted locks and the pending request also. So, when we were talking about the concurrency control mechanism, we have seen two things. One is kind of an log based protocol, another one is the time based protocol. Let us cover that very briefly here. So, each transaction is issued a time stamp when it is going to enter the system, which is unique, and newer transaction have the time stamps which are strictly greater than the earlier ones, which are strictly greater than the previous ones. And time stamps could be based on a logical counter, we can say, in which this real time may not be unique, but we can use a logical counter or wall clock time in order to ensure the uniqueness of the time stamp, we can say. And time stamp based protocols manages the concurrent execution such that the order of the time stamp is equals to the serializability order. And what is serializability? That we have seen in our previous discussions. And we can also say several alternative protocols based on the time stamps are also possible. So, we can say the newer one which has recently arrived will be the one who is going to be rolled back. The earlier ones which are already waiting in the queue should be granted their locks, or something of that kind of policy protocol decision makings, we can say. So, in this lecture we have covered kind of concurrency control mechanism, who is going to take care, how it is going to be take cared, and the two protocols which are available for this concurrency control mechanism. One is the time based protocol, time stamp based protocol, and another one is the lock based protocol. And here is a list of references which is being used for the preparation of lecture. Hope you have enjoyed one. I'll see you in the next lecture. Till then, take care. Goodbye.